Hello, and welcome to a presentation about the Aerospace Village Badge design. My name is Dan Allen, and I have the Twitch handle at CyberTestPilot. How to PCB. I am completely self-taught. I wanted to get into PCB design, and I found the YouTube series by Sean Hiemel, sponsored by DigiKey. It's a 10-part Kycad video series, and it walks you through a very logical progression from zero to hero, how to PCB from start to finish, where you can actually get something fabricated and hold it in your hand that you have designed. I found that video series fantastically helpful, and from there I just launched my inquisitive mind to continue learning and see what I could do in the space. Along those lines, the free open source software tools that I found and utilized throughout this project, Inkscape as a SVG editor for all the graphics, Kycad, the PCB manufacturing software files. I found a module, SVG2 mod. This is a very helpful module to take the vector graphic files that Inkscape would make and then convert them to the Kycad module footprints that would then be necessary. So it was kind of my go-between Inkscape and Kycad, where you can join art and engineering kind of at the same time. It's a command line script and does the conversion for you. I used the Arduino IDE. I stuck with the microcontroller, the ATtiny85. It was a stack I was familiar with. In terms of purchase tools to actually program the microcontroller, I had the SparkFun AVR Tiny Programmer, retails for $16, and then the ICSP Pogo adapter retails for $12, the little kit you can get from SparkFun. The two hardware components utilized to actually program the microcontroller. So we started at the Aerospace Village from just an initial concept, a top-down view of an aircraft. You can see that we had initially the designs for an ADS-B dipole antenna coming out the wings. We knew we wanted an integral antenna that was tuned to the 1090 megahertz frequency to be used as a receiving device for ADS-B messages. And then we had this kind of an additional idea to have additional wire leads being able to come out that could be cut, tuned to different frequencies, lengths to adjust for the frequencies, and so that we can have a mechanism to have additional connections at that point. So from this initial concept design, we have to actually turn this into some engineering and make some trade spaces and concessions to actually get into something that we can actually manufacture. So the initial concept morphed into this two-engine top-down view of a 787 aircraft, a Boeing 787. You can see here that the dipole antennas have been moved to be more aligned with the fuselage. This was just a practical length extension where we could get that perpendicular or parallel rather dipole antenna setup as it ran the entire length of the fuselage. And then from a top-down view, like, let's make it fun and aesthetically pleasing. Let's add the anti-collision lights and some navigation lights, as well as some flight deck lighting. And then use the engines as an opportunity for the SMA connectors. This was really fun because dimensionally it could kind of work out where we scale the engine back from the actual drawing and then kind of use the additional space of the SMA connector to kind of protrude forward as the engine cowling. That was kind of a fun way to play the actual characteristic shapes of an aircraft with the actual components that we were going to need to make the badge functional. So this idea needs to get mapped to a schematic. So here in this box here, we've got the ATtiny85. It's pretty small form factor and also relatively inexpensive microcontroller. And it had the sufficient amount of pin outs that we needed for this project. Down here in the lower left corner, we've got a switch and connection to a battery so that we can turn power on and off to the device. We've got a breakout here for I2C and then ground and power so that we can interact with the microcontroller external or easier. And then we've got the ICSP connection here so it's easy to program the microcontroller. And then the two SMA connectors here and here, so engine on the left, engine on the right. And then the remaining components are simply the resistors and reverse mount LEDs that we use to achieve the lighting effects. As we move on, we need to make the parts fit. This is kind of an interesting trade space. In my limited experience designing PCBs, you've got an idea of what you want things to do and how you want them to operate, but you have a form factor that's limiting, and you need to make sure all the components fit and can be compatible with one another. Real quickly, as we make the parts fit, and this is something that I learned in the design process, it's good to have an understanding of how you want to take the graphic, but eventually it has to be moved to the Kycad footprint module. And so knowing the processes and steps that you have to go through to get to the end state, it is helpful to take just a quick second and walk through the tool that we use to make that Inkscape to Kycad format, and that is the SVG2 mod. So if we go here, this module that I found online, exactly as it states, converts Inkscape SVG drawings to Kycad footprint module files. Command line tool, give it the input SVG that we will design in Inkscape, and then export as we need to. I draw your attention to this because of the layering. What they're talking about here, what SVG2 mod is looking for is a specific set of named layers in the Inkscape file. This is helpful so that we can start to organize how we want the Inkscape files to be organized. So as we make the parts fit, I'll jump over to the Inkscape file itself. These named layers are matching what we want the SVG2 mod. We'll be able to pick up those named layers and then export them to the correct Kycad module footprint. So in PCB land, thinking in layers, there's essentially 4 color opportunities that you get to pick from. There's the color of the copper layer, silver typically in color. There's the solder paste color that you get to pick. Most often that's green, but depending on the manufacturers that you go with, you can make it blue. Blue was the chosen color for the final version of the badge. In addition to that, on top of the solder paste color, you get typically either a color white or black. That's called the silkscreen layer. We got white with this particular manufacturer. And then the other kind of fourth perhaps neglected color is actually the substrate color. So if you could see through the board, it's the color that is in the middle. So it's kind of a translucent, almost yellowish color, but there's opportunities to use that as a fourth color. Thinking in terms of layers, now we have an opportunity to outline that in Inkscape and with SVG2 mod in place, or with an understanding of how it works. The first layer we have selected here is the edge cuts. I'm going to turn on the front copper layer. Here you'll see that this is our dipole antenna. If you can see the value up here, it's 65.173 millimeters in length. There's an equal one on this side as well, and that is to be tuned specifically to the ADS-B frequency at 1090 megahertz. Interestingly enough, the overall length of the badge was more or less dictated by the length of this dipole antenna. We squeezed as much as we could right there, and equally similarly at the top. So this is a design consideration, a constraint. This is one of our bounding dimensions, is to make sure that we have sufficient length for the antenna. For the navigation lights, I've found through experience that using a copper pore indicated by the entirety of the black really kind of helped to highlight or isolate the light that we want to shine through from the reverse mount LED. That was kind of a nice little aesthetic trick. You'll notice this black box here, and that is when it's combined with the mask. You'll see as I toggle them, the Aerospace Village logo, indicating that with the mask here, we would get no because copper would be poured there, but solder screen mask copper would be poured in the entirety of the black circle, but then solder screen mask, the blue, will be absent where the black is here now. So we get the logo to shine through in the same color as our copper pour, which was silver, and then draw your attention to the flight deck lighting. So the mask, this would go through to the substrate, and then because we also in the copper pour, here's the copper, where black is, copper will be, and where the mask is, solder paste will not be. This is kind of an idiom to get used to, and it's even confusing as I vocalize it. Copper layer is where material will go, and then in the mask layer, it's where material will be absent. When you put those together, you're actually going to get a through layer all the way, which is exactly what we want, because we want to reverse light this flight deck lighting, and then also the navigation lights that are present on both edges of the wing. The last decorative layer, and this is a little more straightforward to think through, is the silk screen. So this is just exactly where you want the color white to be printed, is where it will go. And so in this instance, we've got silk screen really helping us outline and sell the shape of leading edge flaps, trailing edge flaps, vertical stabilizer, horizontal stabilizer, overwing doors, just exterior doors. And so this layer is the silk screen. This SVG2, or I'm sorry, this Inkscape is saved as an SVG file and then run through the SVG2 mod converter. And at this point, now we have a Kycad file format that can be used and imported into the next set of steps. Prior to moving things into Kycad, I did want to kind of do an operational check verification that sizing of components would still work. For me, it was easier to print on a 1-to-1 ratio and then just draw in with pencil. This is a rough draft drawing of an idea that I had as we were getting closer to the progressive, final stage form factor. I wanted to really make sure that the SMA connectors, as roughly measured, would aesthetically look correct in terms of replacement of the engine cowlings. I wanted to make sure that the battery could be sufficiently hidden with the retainer clip, hence the battery in the middle of the graphic. My small representation of where the microcontroller approximately will go, and then just kind of holding up some of the reverse mount LEDs that I had chosen, like, will these work out on that edge of the wingtip? Again, one of the constraints was the length of the overall ADS-B internal antenna. Once that was set to the minimum that it could possibly be, do I have sufficient space to still sell the idea of navigation lights here and then anti-collision lights here with sufficient space for battery and power switch? So this was a helpful step to make sure that conceptually, physically, the parts were going to be compatible. With that work done, we were ready to start going into the Kycad viewer. And here we've got the Kycad program running. I've got just the edge cuts selected here as our rough shape outline. We can turn on the front copper. So if you recall from the Inkscape, some of this will look very familiar. What we have now is additional wire traces to connect the dipole antennas, footprints for the SMA connectors, and we can continue adding layers. We can see the back copper layer at the grounding for the coin cell battery. We can start to get some of the there in the back copper layer, the green. We've got our no fill zone, so our reverse mount LED is going to shine through just that window. So to give us the kind of a clear, focused, concise version of what an anti-collision or a navigation light rather would look like out on the end. Similar on the other wing. And then we've got through-hole LEDs. These are white LEDs for the strobe lights. And then we've got a similar kind of layout, reverse mount on the back copper pour, a light for the flight deck lighting, with an understanding that the light will, as it's diffused, will kind of really go out and cover the entirety of this window outlined by the front copper pour. All of these things are working together for us. Add to that the silk screen layer, the back silk screen layer, and we are starting to get a badge that has all of the components lined up, and we are getting very, very close to fabrication. Something I like in the Kycad viewer, and I found this very helpful, is the badge 3D viewer, or just the 3D viewer, but in our case this is the badge now. And so this was helpful to view, set the blue color so I can see the final form factor. You can start to see that the silver is coming through for the aerospace logo Village. We've got our hole cut out here for the anti-collision light. We rotate this. All the components are fitting. We've got reverse mount LEDs. The microcontroller with the ISP breakout for programming it. We've got the switch. And everything is nearing completion at this point. So we have the Kycad layers. We bundle up the files from Kycad. They're called the Gerber files. You bundle up the zip files, you send them off to the manufacturer. You wait a number of days, weeks, and then you get your first version back. Always a nail biter to see if it actually works the first time. In this case, pleasantly surprised, version 1 worked. It was incomplete in that it didn't have initially like a battery switch or the external antenna connectors, and this was just kind of in the interest of a compressed timeline to make everything work. Some of those initial considerations had just been like foregone, like let's get something working. This did have the internal antenna, did connect it, wire it up, everything worked. There were no shorts. But now in the redesigned version 2, we've switched to the blue color, the final form factor. We've added the terminal connectors for the external wires. Here, if you can see these are spring loaded so that you can load a wire up onto either side. And then it's wired now to one of the SMA connectors. On the back, showing it's got the switch and another design consideration. I wanted everything to be, to the extent possible, surface mount to keep kind of all the business end on the back end of the badge, or the battery, and all the other components are. The one concession I made, and this was intentional, was the through-hole components for the spring-loaded antenna connectors, and that was just to provide a mechanical advantage so that these things are fairly rigid. I was concerned that with the surface mount component, if something got tugged on it, the whole component could come off. Through hole kind of solidified that. So it's still on the back side of the badge, it's still fairly concise. And then the front, of course, the top is a clean badge. The only exception is like the connections where the SMA, as they're a side mount component, they have a mechanical top and bottom part, which is fine in case there's any, again, mechanical tugging on there. So prototype version 2, we had it, wired it up, hooked it up to an RTL SDR dongle, ran the dump 1090, and lo and behold, ADS-B in traffic in my local area was being captured and picked up. I was like, this is amazing. This is really fun. Again, for a first time badge manufacturing process, new to the industry, new to the concept of even doing it myself. Like something I had designed was working to effectively pick up aircraft. It was the antenna, but it was also aesthetically an airplane, so it's kind of iconic in that sense. And that was a lot of fun and very rewarding. It's working. So we've got the navigation lights on. The strobe lights are pulsing. That was fun to program, kind of just from my experience watching aircraft at night. The approximate pulse cycle of how anti-collision lights work. So that was a fun little event to code up on the microcontroller. And then the really super cool version is at night, where you really get the highlight of the navigation lights. And then, of course, you really get the selling of the anti-collision lights. So, questions, if you are at all interested in making this for yourself. The entire thing has been posted to my AV Badge 2020 GitHub repo. In here, we can see the entirety, all the components, everything that I've gone through is stored in this repo. So the pictures that you've just seen, kit assembly instructions, programming with the Arduino. We even had a contributor add a lanyard modification so you can wear the badge easy enough with a chain or a rope of some sort. All the files are here if you want to modify it, make recommendations, pull requests is certainly advised, requested. Please do so if you want to make this better. In terms of Kycad, if you're interested in making this, if you don't want to go through the whole hassle of redesigning everything yourself, you are more than welcome to grab this Aerospace Badge version 2.zip. If you take this zip file and send it to the PCB manufacturer of your choice, they will be happy to manufacture a PCB that does exactly as we've walked through. And then in terms of the parts list, we've got the entirety of the, this is the parts, all the parts, the CSV, and then the BOM. That may not load, that's the XLS. So GitHub's not going to show me that, but you can download that. We made all the purchases from DigiKey, so all the part numbers and links are referenced relative to DigiKey. Great resource to get all of the obscure individual components for the badge. And approximate DigiKey purchase price for all the BOM is about $13. And then again, depending on your PCB manufacturer, you probably get 5 badges, just PCB, probably delivered to your door for anywhere in the ballpark of like $10 to $15 at the low end. Might take a month to get, but it's available. But that is a walkthrough of the Aerospace Village Badge presented at Defcon Safe Mode. Thanks.
So that's it. Well, thank you for being here. The talk was amazing. We have a lot of different projects here in the aerospace, and we really love to see how the badge of the village was done. So amazing. We are now in the Q&A. We have in the right the questions of the people that is watching the talk. So in case we have anything here, we can read it and just answer it. Okay.
Yeah, thank you very much for having me.
Okay, Dan. I will have a question for you. How much time you've been designing the PCB badge?
That's a great question. So I consider myself like I'm still learning. I feel like with years of experience, I could probably do that same badge, like recreate it probably in like a 15 to 20 hour, kind of timeline. But given that I was still learning how to do it, like exploring and iterating through it, probably that badge took every bit of like 80 hours. Like when you add up, hand drawings to what is the microcontroller I'm going to pick, to like coding it up. it gets pretty involved. It ends up being spread out over multiple weeks.
Wow, great. And how much iterations do you have in the PCB? I mean, how many times you send it to to make the PCB
Yeah.
and need to make it again?
Yeah, so I like again from trial and error. The that badge was I think the fifth PCB that like I had ever done myself. So like in previous iterations, it was just me tinkering with the whole idea of manufacturing and design of a PCB. When the Aerospace Village needed a volunteer to make a badge, like, all right, I've got a skill set, let's bring it and help out. Um, that said, we were under a time crunch, so I knew that I couldn't have a whole lot of iterations with the manufacturer because it takes about the manufacturer I was using about 10 days to come back, from manufacturing to mail back to my house. So um, I did like a whole bunch of work to make sure version one was good, and then sent off version two as a low batch, but I was expecting and hoping, fingers crossed that version two was going to work. It did. And so then we took like, I think I ordered 10 for version two, and then we went up to full volume for the order. And as soon as I was watching the mail, so as soon as the board got there, it was like my afternoon. I had to do this thing right now to make sure it works so that in like an hour I can, commit the order to the bigger number.
Oh, that's great. I think that we don't have so much question now, but I have one more. I think that with this question we can end. So we have time to have the following talk. Dan, you explained a little bit in your talk, but how this idea grew up in the village. It was like a necessity. It was something like a challenge, and how it started this project.
Yeah, so the Aerospace Village, I think, had started initially at the Defcon conference, and the Defcon conference has a big badge life, following. And so the Aerospace Village initially was just the Aviation Village, and then as it relaunched, for year two, it was the Aerospace Village, and it was getting bigger, and it was getting more name recognition, more branding. Like, hey, from the volunteer corps, like we should have a badge, like all the other villages, like we should have a badge. And I was hungry. I was like, yeah, like this is like a good volunteer thing that I can, go sink my teeth into and help the village out. And I kept asking, like, hey guys, like I want to help. I want to help. Like, where's the team? Where's the team? And they're like, there was ideas, but not necessarily like the capacity or capability for people to do it. So I was like, all right, I've done this in my free time, at small scale. Like, let's just grow up. Let's go do it. And so a
But
lot of fun.
but it was great. A lot of
Yeah,
people enjoy it.
yeah, and
Um,
such a thrill too, like to be at the conference or to like have someone wearing it, and you're like, oh my goodness, like I did that. Like that's cool. That's like a super rewarding.
okay. Well done. Thank you so much for being here in Ekoparty in Patagon Space. It was great to have you. Thank you so much to showing this crazy idea to show us how the PCB was designed. For sure, we will have some question for you later. I'm sure about that. So I will share with you by email or maybe at the I don't know any other way. So thank you so much for being here.
Yes, thank you very much for having me.
Okay, bye, man.